You throw a ball in the air, you know it will come down. You know the path it will take. It's a clean arc, predictable and simple. You don't need to be a physicist to know this. You just know. But underneath that simple knowledge is a set of rules. We call them the laws of physics. Gravity, air resistance, momentum. These rules govern the ball's journey. They calculate its position at every moment. The universe seems to follow these rules perfectly, without exception. This leads to a strange question. A deep one. If the universe follows rules so perfectly, like a computer running a program, then could it be just that? Is it possible that our entire reality from the ball falling to the galaxy spinning is a kind of calculation? And if it is, could it be just one calculation among many others that are running right now? Let's be clear about what we mean by calculation. We're not talking about a giant cosmic calculator with a screen. A calculation is just a process. It takes an input, follows a set of rules, and produces an output. A simple computer program does this. A game of chess does this. The initial state of the board is the input. The rules of how pieces move are the program. The next state of the board is the output. This happens over and over. The universe works in a similar way. The state of the universe right now is the input. The laws of physics are the rules. The state of the universe a moment from now is the output. This process has been running since the Big Bang. Every particle, every star, every interaction is a step in this unimaginably vast computation. It's a strange thought. It makes the universe feel less like a place and more like a process. An unfolding story written in the language of mathematics. This idea isn't new. In the 1960s, a man named Konrad Zuse, who built one of the first computers, suggested the universe might be a type of cellular automaton. Think of a grid, like a checkerboard. Each square can be on or off, black or white. You apply a simple rule like, a square turns on if two of its neighbors are on. You run this rule over and over. What starts as a simple pattern can evolve into something incredibly complex, something that looks alive. Zuse wondered if the universe was just a much more complex version of this, with simple rules at the bottom level creating all the complexity we see around us. Later, the scientist Stephen Wolfram explored this idea in great detail. He showed that you don't need complicated rules to get complicated results. Some of the simplest possible programs can produce patterns that look random, organic, and unpredictable. They can create a kind of complexity that rivals nature itself. So the thought is, maybe the fundamental laws of our universe are actually very simple. But by running them for billions of years in an unimaginable number of particles, you get the richness of reality. You get galaxies, stars, planets, and us. If this is true, if reality is a kind of computation, then you'd expect to find clues. You'd expect the universe to have certain properties that look, well, computational. And when we look closely, we find some strange things. First, there's the role of mathematics. It's been called the unreasonable effectiveness of mathematics. Why should abstract concepts, things we invent in our minds like imaginary numbers or complex geometries, be so good at describing the real world? It doesn't have to be that way. And yet, from quantum mechanics to general relativity, our most advanced physics is pure mathematics. It's as if we are slowly discovering the source code of reality. The universe seems to be written in a language we can understand, and that language is math. In a computational universe, this makes sense. The underlying logic of the system would be mathematical because computation itself is a mathematical process. Then there's the fact that the universe seems to be pixelated. When you look at a computer screen, it looks smooth from a distance. But if you get close enough, you see the individual pixels. It's not a continuous image. It's made of discrete, tiny units. Quantum mechanics tells us that reality is like that too. Energy comes in little packets called quanta. There's a smallest possible length called the Planck length. There's a smallest possible unit of time, the Planck time. You can't have half a Planck length. You can't have a distance smaller than that. It seems the universe has a fundamental resolution. It's not infinitely smooth. This is exactly what you would expect if reality were being computed on some kind of grid, some kind of system with a finite limit. Another clue is the speed of light. Nothing can travel faster than light. It's the ultimate speed limit of the universe. But why should there be a speed limit? In a computation, this makes perfect sense. It's a processing speed. Information can only be passed from one part of the system to another at a maximum rate. The speed of light is the speed at which the universe can update itself. It's the clock speed of the cosmic computer. The effects of a cause can't spread faster than the system can process them. And finally, there's a weirdness in quantum mechanics itself. And particles, like electrons, don't seem to have a definite position until you measure them. Before that, they exist in a cloud of possibilities. It's as if the universe doesn't bother to calculate their exact position until it's absolutely necessary, until something looks at it. This is similar to how a video game works. A game doesn't render the details of a city on the other side of the map until you actually go there. It would be a waste of processing power. It only calculates what's needed when it's needed. Could the universe be doing the same thing? Is it conserving its computational resources? It's a wild idea, but it's a parallel that's hard to ignore. So if we accept this for a moment, if we say the universe is a calculation, it begs the next obvious question. Where is the computer? Where is this all running? There are two main schools of thought here. The first is the one you see in movies like The Matrix. It's the simulation hypothesis. This idea suggests that our universe is a simulation running on a computer in another, more fundamental reality. Someone or something built a massive computer and is running a program of our universe. Maybe it's a scientific experiment. Maybe it's a form of entertainment for a post-human civilization. Maybe they're looking for answers to their own questions about reality. The philosopher Nick Bostrom made a compelling argument for this. It goes something like this. If you assume that a civilization can reach a point where it has enormous computing power, and that it might want to run simulations of its ancestors, that's us, then it's likely they would run many, many such simulations. If you can run one, you can run thousands or millions. If that's the case, then the number of simulated minds like ours would vastly outnumber the number of real minds in the original reality. So, based on pure statistics, it's more probable that we are one of the many simulated minds, not one of the few original ones. This idea is both fascinating and unsettling. It means our reality isn't the base reality. We are living inside something else, but it also comes with a big problem. Who built the computer of the simulators? Are they also in a simulation? It can lead to an infinite regress, a never-ending stack of simulations within simulations. This is why some physicists prefer a different idea. The universe isn't running on a computer. The universe is a computer. There is no outside. The hardware and the software are one and the same. The very fabric of space-time, the particles and the forces that govern them, are the components of the computer. Every particle stores information. Every interaction between particles is a step in the calculation. An electron knows its spin and charge. When it interacts with a proton, they are processing that information. The result is a change in their state, a new piece of information. The physicist Seth Lloyd called this the computational universe. He calculated the total amount of information the universe could hold, and the total number of operations it could have performed since the Big Bang. The numbers are astronomical, far beyond anything we could imagine building. In this view, the universe isn't simulating anything. It is simply computing its own evolution. The Big Bang was the moment the program started running. The laws of physics are the algorithm, and the universe we see today is the result of 13.8 billion years of processing. This idea is more elegant in a way. It doesn't require a simulator or a higher reality. It just says that at its most fundamental level, reality is information. The universe is a story that tells itself. It is a calculation that calculates itself. The rules just exist, and the process just runs. There's no why, there's just is. This brings us to the second part of the original question. If our universe is one calculation, could there be others? This is where the idea of a computational universe connects directly with the idea of a multiverse. If the universe is a program, then you can imagine running that program with different starting conditions. The Big Bang set the initial input for our calculation, but what if you change that input just a tiny bit? What if there was slightly more matter, or slightly less dark energy at the start? You would run the same program, the same laws of physics, but you would get a completely different result. You would get a different universe. This is one version of the multiverse, an infinite number of universes, all following our laws of physics, but each starting from a different random seed. Some would be similar to ours. Many would be empty and dead. Some might be wildly different. Each one would be a separate run of the same cosmic program, but you could take it a step further. What if you didn't just change the starting conditions? What if you changed the code itself? What if you changed the laws of physics? You could have a universe where gravity is stronger or weaker, a universe with different fundamental particles, a universe with 4 dimensions of space instead of 3. Each set of laws would be a different program, and each program could be run with countless different starting conditions. This creates a multiverse of unimaginable scale, not just many universes, but many types of universes. An entire landscape of possible physical realities, each one a different calculation. Some physicists who work on string theory believe something like this might be true. They talk about a landscape of 10 to the power of 500 possible sets of physical laws. Our universe is just one of those possibilities, one that happens to have the right settings for stars, planets, and life to emerge. We live in this one because we couldn't exist in the others. So the idea of the universe as a calculation doesn't just describe our reality. It provides a framework for imagining all possible realities. The multiverse is no longer just a collection of other places. It's a library of all possible computations. Some are simple, producing nothing of interest. Some are complex, like ours. Maybe some are even more complex, producing forms of existence we can't even imagine. Of course, this is all highly speculative. It's a powerful and compelling idea, but it comes with a lot of problems and objections. The biggest one is that it might not be testable. Science relies on making predictions that can be tested by experiment. How can we ever test if we are in a simulation? Some have suggested looking for glitches in reality, places where the simulation breaks down or the resolution of the universe becomes apparent. Maybe high-energy cosmic rays behave in a way that suggests they are hitting the grid of space-time. But so far, we have found no evidence of this. The universe seems to be a very well-made program with no bugs. Another major objection is the problem of complexity. To simulate a universe like ours, you would need a computer that is more complex and powerful than the universe itself. Where would such a computer come from? If you say it exists in a higher dimensional reality with different laws of physics, you are just pushing the problem up a level. You haven't really answered it. The view that the universe is the computer avoids this, but it still leaves you with the question of where the rules, the program itself, came from. And then there is the deepest, most personal question of all. If we are part of a calculation, what does that mean for us? For our consciousness, for our free will, are our thoughts, our feelings, our choices just predetermined steps in a massive algorithm? Is my love for my family just a subroutine? Is my sense of self just an illusion generated by the processing of information? This is where the line between physics and philosophy blurs completely, and maybe the answer is that it doesn't matter. Your experience is what it is. The pain you feel is real to you. The joy you feel is real to you. Okay. Whether the substrate of that experience is a brain made of carbon atoms or a process running on some unknown cosmic computer, the experience itself is unchanged. A character in a novel doesn't know they are made of ink and paper. Their story is real to them within their world. Perhaps our reality is the same. We are real within this calculation. The rules of this universe are the rules that define us. Our freedom exists within those rules. You can't choose to fly by flapping your arms, because the laws of physics in this calculation don't allow it. But you can choose what to say, who to love, what to believe in. That freedom, that experience of consciousness might be an emergent property of the immense complexity of the calculation happening in our brains. It's not a violation of the code. It's a beautiful and complex result of it. So where does this leave us? Is the universe a calculation? We don't know, and we may never know for sure. It's an idea that sits at the very edge of what science can tell us. It's a mental model, a lens through which to view reality, but it's a powerful one. It helps to explain some of the deepest puzzles of physics, like the role of mathematics and the strange nature of quantum mechanics. It provides a natural home for the idea of a multiverse, transforming it from a strange fantasy into a logical possibility. And it forces us to confront the most fundamental questions about what it means to be real and what our place in the cosmos might be. Thinking of the universe as a calculation changes your perspective. You look at a tree, and you don't just see a tree. You see the result of a billion-year-old algorithm for survival and growth, a complex pattern generated from simple rules of biology and chemistry. You look at the night sky and you don't just see stars, you see the state of a massive computation, a snapshot of an evolving system. It doesn't make the universe less beautiful or meaningful. In a way, it makes it more so. It suggests that complexity, beauty, and even consciousness can emerge from simple rules followed patiently over cosmic timescales. It suggests that our existence is not just a random accident in a meaningless void, but a possible outcome of a logical, ordered process. And if we are just one calculation among many, it's a humbling thought. It means our entire cosmos, everything we've ever known or will know, might be just one instance of a program. Out there in the vast space of possibility, countless other programs are running. Other universes with other laws, other histories, other forms of existence. It makes our universe feel both incredibly precious and, at the same time, not all that special. Yes, we are one expression of a much larger, and perhaps infinite creative process. We may never get to see these other calculations. We are bound by the rules of our own program, but the idea that they might exist expands our sense of what is possible. It tells us that our reality is just one answer to a question, and there are countless other answers out there playing out in the dark. The universe isn't just a place, it's an idea, and it might be just one idea among many. The great computation continues, and we are, for a brief and shining moment, a part of it. And maybe that's enough.